So in a previous lecture, we qualitatively derived the uncertainty relation by saying that if we want to model a localized particle such that delta x is not infinite, right? The range of positions is not infinite, so that it can represent a localized particle. So delta x equals finite. Then we needed a finite range of wavelengths, and so this must not be equal to must not be equal to 0. So delta lambda is equal to finite, and that translates to a delta p momentum. Delta p also equals finite, and so we say that delta x times delta p, the range of position times the range of momentum, ends up being greater than or equal to some number. Let's just call it a. Let's get a sense of what that a is by thinking of the particle in the one-dimensional prism. So the particle is confined between 0 and L, and we know that the energy levels are, we derived this, En equals n squared, right, from the boundary condition here, that the wave function, which is proportional to the sine of x, has to go to 0. Sine of KL goes to 0. We get KL equals n pi, and so that translates into an energy which is p squared over 2m, being n squared h squared over 8m L squared. And as I just said, the energy is p squared over 2m because it's kinetic, and so we can find the momentum. Right, the momentum is plus or minus the square root of 2m times En, which we're going to put this in here. So we'll get, we take the square root of this, we get nh, so we get plus or minus nh. The m cancels with this m, and the 2 and the 8 produce 1/4, and so we get a factor of 2 here, and then we have an L squared, which becomes an L. So those are the possible values of momentum for each value of n, and therefore we can say that for a given value of n, delta p for Pn is equal to, right, the range is the maximum minus the minimum, so that is nh over 2L minus a negative nh over 2L, and that's just nh over L. So there we have a finite range in momentum in an energy eigenstate, and so we can say, right, let's estimate the range of position. Well, the particle is forced to live between 0 and L, so that range is L minus 0. So that's L times, that's delta x. This is delta p, so we have nh over L, and that gives us nh, and so we can conclude that we have just shown that delta x times delta p, the minimum that this can have, right, so n can increase from 1 to infinity, so this has to be greater than or equal to the minimum, which is n equals 1, which is h. So we've derived the uncertainty relation in terms of ranges of position and momentum. Right? We're not using standard deviations here.